Now let me go to the, okay, now I am here. This is working, yeah. Okay, so my name is Ivan Arraut. I graduated from the University of Osaka, actually, in Japan. Actually, 11 years ago, I think, already, 2014. Under the supervision, I had two supervisors, Yutaka Hosotani, who was particle physicist, and Hideo Kodama, who was in the KK, High Energy Accelerator. So now I'm working at University of San Jose, Macau, where we are launching the science more serious right now. Then beside that, we have some organization called Crusade. We have a research team there, and we have created the Macau Quantum Technology Association recently with the purpose to disseminate and encourage to the young people in Macau to follow the path of science, because as you know, Macau science is not that popular, so we are working on it for going to the schools, telling to the young guys to please follow science because it's interesting, this and that. And today I'm going to talk about symmetry arguments for dealing certain problems in cosmology and particle physics. So it's some kind of collage of different topics. In some of them I will go quick because I presented partially last time I came one of them, so I don't have to talk so much about it. So first I will make a review about symmetries. What is a symmetry? Well, any transformation leaving the system invariant. For example, if I rotate this ball, the shape will not change. That's a global symmetry. If instead I take a point of the ball and I rotate it, the ball will get deformed. So that's a local transformation, and it becomes a symmetry if I introduce a gauge field, which restores the shape of the ball. No? So I have to introduce an additional field for organizing the symmetry again. And that's what we do the whole time. For example, the photon field in QED is an example of a gauge field. And of course, the boson C and W in the electroweak theory, etc. And we did with internal and external symmetries. Of course, internal symmetries are those who are using condensed matter physics. External symmetries usually are space-time symmetries. So another example where you will see this in a group theory book, this is the diedral group. I will not deal with this, it's just an example. When you fit the triangle around this axis, you obtain the same triangle. This is another example. So any symmetry over the action, if we have an action, leave the action invariant up to total derivative, no? So that's the notion of symmetry, mathematically speaking. So the symmetry is also important in physics. Why? They govern the interactions. If we change the symmetry in certain interactions, their behavior will be different. So it will not be the same interaction anymore. Symmetries are connected with conservation. Symmetry under translations is conservation of momentum. Symmetry under time translations is conservation of energy. Symmetry under rotations is conservation of angular momentum. Symmetries explain the behavior of a system. When broken, particularly spontaneously, they are related to quantum phase transitions, another interesting phenomenon, like the Higgs mechanism and so on. So first, I will talk about general relativity, which is the theory of gravity for excellence, which is full of symmetries also, different kinds of symmetries. It's diffeomorphic, it's invariant under coordinate transformations. But besides that, when we find the solutions themselves have some symmetries associated to the space-time, rotational, translational, whatever. So general relativity has been a successful theory all these years. It has never failed until now. All the experiments are supported GR classically. Quantum mechanically, we know that we need a new theory. Of course, because we have the singularity of the black hole, the center, where general relativity just gets lost. Different to the apparent singularity of the event horizon, which is just a coordinate singularity you can remove by coordinate transformation. And of course, there are certain phenomena that we expect to appear when we consider quantum gravity. Hawking radiation is a quantum effect, but it was derived semi-classically. I will talk a little bit about it later. in the sense of symmetries also. Successes, or the successes of GR, we have gravitational waves represented two Nobel Prizes actually. One Nobel Prize was in 2017 because of the LIGO detection. I think everybody remember that one. Black hole collisions or so they could detect. But LIGO is focused on high frequency events, violent events, low frequency events they cannot detect. For example, for low frequency events, you need another project. They call it LISA. It was supposed to be launched by NASA initially, then it went to the European agency, and now I don't know who has, I think nobody has budget for that right now. But the idea is to detect low frequency gravitational waves sources with that project. Still is not running. Gravitational waves for low frequency are more stable. I mean, they represent more stable systems because the high frequencies are really catastrophic events or so. And of course, the other Nobel Prize related to gravitational waves was the Hall-Taylor in 1974 when they could measure the rate of decreasing of two bodies rotating around each other, a pulsar binary, and the rate of approach coincide with the predictions of general relativity. So that was the other Nobel Prize. So we knew gravitational waves indirectly a long time ago. We knew they exist, but we wanted to detect them directly. That's what happened. Of course, everybody knows that we just studied from textbooks of GR that the precession of perihelion Mercury was the first evidence that Einstein found. The first prediction he did correctly with GR. By the time when Hilbert almost take the glory away from Einstein, because the story is that there was a seminar, Einstein gave the seminar and Hilbert was in the audience. Hilbert saw the results partially. Einstein had doubts in the second term of the equations. He didn't know it was 1/2 or just one. Then Hilbert took the problem, used the variational principle, which Einstein didn't know, and derived it correctly 1/2. Then Einstein, I think that when Einstein saw it, of course, he realized what 1/2. But fortunately for Einstein, Hilbert recognized that the theory was from Einstein. So that's why we call the Einstein-Hilbert action right now. Besides all these predictions I mentioned, we have gravitational lensing. Einstein became famous internationally is because of the famous eclipse, the famous predictions which were measured during the eclipse, the solar eclipse, by Eddington. But by the time people didn't trust in the Eddington results because they think that he manipulated the results because he wanted to support Einstein. So that's why there was a second expedition with 6 different teams around the world, and all of them measured. There was an unlucky team that couldn't measure anything because the clouds didn't allow. But at the end, all of them agreed that, yeah, the gravity deviated the light, deviation of light. And we use now for measuring dark matter, the effects of dark matter on the galaxies, gravitational lensing is called this part of GR. Dragging effect, I'm not so sure, but I think that it was measured experimentally, at least that's what they say from some years ago. They put some satellite many years and they see how much it was deviated due to the dragging effect. Well, of course, these effects are more evident in the neighborhood of a black hole. Near a black hole, of course, the dragging effect. It's like the space-time is a fluid. If you rotate an object, the fluid will move now. So that's another issue. So there are many problems, including gravity, but there are 2 problems. One is dark matter, dark energy. They represent together almost 96% of the content of the universe. Dark energy is 73 or so percent of the universe. Dark matter between 23 to 26% of the universe. So people are investigating what is it. Dark matter generate attractive effects, have the tendency to attract more. The galaxies rotate much faster than what they should. The lights deviate much stronger. The deviation angle is larger than what it should be. And dark energy is the opposite. It accelerates the universe, expands the universe. It has the tendency to separate it. In fact, there are experiments that intend to measure this competition between dark matter and dark energy effects at some scales. There are some scales where the attractive and repulsive effects that are competing for the formation of a structure, and this is measured by some big experiments. Usually, the dark energy survey of these guys involved in. I have some colleagues involved in this issue, so that's why more or less I know that thing. Okay, dark matter represents about 30%. Dark energy, I will take it as a vacuum energy here. Of course, there are many possibilities, but I will take it as a vacuum energy. The problem of dark matter it was discovered when some guys, these guys, realized that based on the luminosity measures, they can calculate the content of matter of a galaxy. And based on the content of matter, the galaxies should rotate at a certain speed. Everything you see in the universe, if it's rotating around each other, is stable. Let's put it this way. The moon, well, it's not exactly rotation, but let's imagine that the moon rotates around the Earth. If it rotates too fast, it will escape. If it rotates too slow, it will fall. So at the end, there is an equilibrium between attraction and repulsion. In the galaxies, it's the same. The reason why the galaxy can keep itself is the stability it represents. If it rotates too fast, it should disappear. No, it should explode. If it rotates too slow, it should collapse. So when these guys measured, they realized that based on the luminosity content, the galaxy rotates too fast. Then there must be something there generating an additional gravitational effect, and they call it dark matter. Dark matter is hypothetical matter that you put with the hand such that you can make the predictions in the galaxy. And this is not the only evidence. The galaxy rotation curves is not the only evidence. This is but it should happen in agreement with Newtonian gravity, because at the galactic level we have weak gravity. The gravity is weak, so we can use Newton. But instead, what we observe is this: the farther you are, the objects still have the tendency to keep that velocity of rotation. So this is an issue. So when people deal with dark matter, of course, they try to put additional matter here with the hand. They invent some profiles of matter, and they analyze some phenomenology, even around black holes. Some people put in the black hole sometimes dark matter, and they try to investigate what happened around the black hole. I have seen these kind of papers, etc. But of course, nobody knows what is dark matter. And the guys who put this by hand here, they think that dark matter is a problem of particle physics, that it should appear eventually somewhere in some accelerator. So, well, this is an example of lensing. Of course, the light is deviated by the presence of gravity in a galaxy. And this is more or less the content of the universe I represent. Well, these are the Friedman equations, which represent more or less the content of the universe. Normally, the universe is flat, so approximately flat. So this is zero. This is the spatial curvature. This is when you use the Friedman-Lemaitre-Robertson-Walker, and you introduce it in the Einstein equations, and it depends which epoch you are analyzing. Dark matter also appears, it should appear as in the CMB. I am not so much into the CMB, but I know it has some effects there. And it's understood that the galaxies exist right now, and they were formed fast enough for existing now because of dark matter. So, I mean, if there's no dark matter, the rate of formation of galaxies will be much lower. Then that's another evidence. Now, dark energy is 70%, is this area. And of course, there are plenty of evidence. It was discovered in 1998 when some guys realized that the universe is not only expanding, but also accelerating. When Einstein generated the Fell equations, his equation suggested that the universe is dynamical, expand or collapse or whatever. So he put a constant for keeping the universe static because by the time they believed that's what they could observe. They saw a universe static. Well, that static universe is unstable. So, I mean, it had failed anyway in any model. So subsequently, Hubble realized that the universe is expanding, and then Einstein removed the cosmological constant, as is known today. Then in 1998, after these guys realized that the universe expand accelerated, they introduced again the same cosmological constant of Einstein, but with the opposite sign for accelerating the universe. So if you change the sign of the cosmological constant, you obtain either de Sitter or anti-de Sitter universe. Anti-de Sitter, which is very popular in string theory, for example, for the gauge gravity duality people, and so on. So the universe is expanding. We introduce the cosmological constant here, but we believe, what is the origin of this term? Many people believe it's vacuum energy. Other people think that they have to modify gravity, etc. I mean, there are plenty of proposals around. This is more or less the action, and this is the theoretical prediction. The theoretical predictions suggest that the vacuum energy density is scaled to the 4th power of this. This is 120 orders of magnitude larger than the observation. And of course, the vacuum has energy. The vacuum creates and destroys pairs of particles, particle, antiparticle permanently, positron, antipositron, electron, electron, positron, proton, antiproton, particle, antiparticle, are created and destroyed permanently. So the dark energy is inspiring the vacuum energy, of course, but the vacuum energy has been detected actually. We had the Casimir effect. It's an example of the fact that vacuum energy in fact exists. You put two parallel plates, those two plates in vacuum, they perceive some force between them. And when we go to quantum field theory and we use the algebra of the quantum harmonic oscillator, which is the algebra we use for quantizing the fields in QFT, let's assume the scalar field, the Klein-Gordon field, for example, you quantize, you impose this algebra. You either impose this or impose the algebra of the quantum harmonic oscillator and expand the fields in positive and negative frequencies. And when you input that here, you obtain the algebra of the quantum harmonic oscillator. It's exactly the same, one way or the other. You have to impose something. So the point is that when you do that, the vacuum has energy. And actually, it's here. When you derive the Hamiltonian, this is the particle number operator. If this is 0, this term survives. And this term, if you integrate, gives you an infinity. In quantum field theory, it doesn't matter. You can drop the infinity because we don't care. It's just a reference point. But in gravity, it matters because in gravity, the energy is a source of gravity. Let's say energy, equivalence mass energy, which Einstein proposed is one of the principles imposed by the time, going from special relativity to general relativity. So, what's the solution of this problem? How to decrease 120 orders of magnitude, or from the 0-point quantum fluctuations? That's a good question. Or we modify gravity. So I went directly to the grain. I went directly to the calculation. This is the calculation we do. Vacuum energy density, you integrate all the modes. This is a triple integration actually. When you integrate this, omega is proportional to k. This gives you 4 pi k squared decay. So there's a k cube here. When you integrate, it gives you a k4. But you have to impose a cutoff. And the cutoff is at the Planck scale level. It gives you a maximum frequency or maximum wave number. And that's 120 orders of magnitude larger than what is observed. So what went wrong, then I proposed some possible solution. It's published already in 2 papers, one in Modern Physics Letters A and the other European Physical Journal C. Because in one I deal with the static case, in the other I deal with the Freeman Lemaitre Robertson Walker, where the solution appears more natural. let's start from the Friedman-Lemaitre-Robertson-Walker and the de Sitter universe. Let's say when all the metrics are ansatz, no? In the ansatz, you have to assume some symmetries. Then you impose those metrics in the Einstein equations. And there are some symmetries to impose, and then we can work with it. So in this case, you can find the conserved quantities, and then you calculate the conserved quantity related to the rotation, which is the angular momentum. You obtain this. This is the conserved quantity. This will be the angular momentum, but it's related to the derivative of phi with respect to lambda. And then I can solve the phi here and integrate. So I found a maximum angle covered by something, which I don't know yet what is it. Then, of course, I impose here the energy time uncertainty principle. T, it has to go like 1 over E. This also lambda is proportional to the time also because it's the affine parameter, which is related to the proper time, which is coincides with the ordinary time here. And R is fixed because in this coordinate system, you put the galaxies or the objects in the manifold, and the manifold expands in time. So in reality, the variable here is the time. So you don't touch the space here. So initially, I did the calculation expanding the Hubble constant like this, like everybody does, and I obtained this with an error function. And the error function was telling me that there was a tendency to obtain zero angle for high frequency modes. And more angle for low frequency modes. That gave me some clue. But then after, I went further, and then I found what is necessary to occur for obtaining the right value of the energy. And later I will explain why the angle is so relevant. Then I realized that the Hubble constant should change in this way. And more or less, that's what happened in each epoch of the universe. In matter-dominated, in radiation-dominated, the Hubble constant always changes in this way. So if you impose that condition in this integral here, then you obtain something like this. Of course, with the argument of the uncertainty principle and so on. You think this is telling you something. It's telling you that high-frequency modes, they don't cover so much angle. So when the pairs are created in the vacuum, particle and antiparticle, they select a plane, they rotate around each other. But if they are done by heavy pairs, they don't live so long. So they cannot cover so much angle. They will not contribute so much to the integration. But if they are low frequency modes, infrared, they live longer and they can cover more angle. So this is what it's telling me this result, and I have to impose that in the integral. In the vacuum energy density, I have a triple integration. It's given by this. The first integration is on theta. It gives me 2. It gives me a 2. Because the sine of theta, the theta gives me 2. That angle represents the plane where the pairs are created. The other angle is related to the angular momentum. It's where the constraint appears. Then I integrate from 0 to phi max. Well, phi max is the angle which I just derived. It's emerging from the symmetry arguments of the metric itself. And I impose it here. Bang. When I impose that here, since it is scaled like 1 over k squared, you know, calculus 3. I don't know in which year you see calculus with 3 integrations, triple integral, but somewhere. When I impose it here, it will cancel this k cube. At least it will go like k only. And at the end, I will obtain a result which is, I think this one, like this. And this result is more or less, of course, we need to analyze it deeper. It's more or less what you have to obtain as observation. That's more or less what the experiments are given to you, up to some free parameters, obviously. I obtained these 2 publications in that, and this is the phenomenology explained. I mean, you have the particle and antiparticle here rotating around each other in a process which they start to rotate until they annihilate again. No? This happens permanent in the vacuum. So if these pairs are too heavy, they represent ultraviolet modes, they will not rotate so much. So it will go from 0 to almost 0 here. 0 to 0, it will not contribute anything to the integration. But the light modes, they will cover more. So now, how do we know that this is correct? Well, if there is an experiment, it's possible to design an experiment suggesting that it's true that the UV modes don't cover so much angle and the others cover much more angle, then that would be a big thing, a big issue related to this result. No? So this is more or less the solution I propose. And now, yeah.
So can you elaborate more about this this coverage angle? Where does it come from? Do you have like down your environment?
What happens is that you have some killing vectors. Well, when you impose, you have a space-time, you have a timeline killing vector, and you have this rotational killing vector. So I have the rotational killing vector is 0, 0, 0, 1. Then I convert that vector to one form. No, I have to use the metric. So when I use the metric, of course, it will scale. These two guys will appear now, which is what happened here. Well, it appears as a squared, but it's the same. This is a squared anyway. Yeah. So that's why you see these two guys here. And after, of course, you have to contract that one form with the derivative of the coordinate with respect to the affine parameter, which is what happened here. And then after, of course, this is a conserved quantity. But then I want to solve the angle. I mean, for every conservation, there is some constraint appearing in the variables, no? Let's put it in this way. I mean, if the speed of light is constant, something else has to change, no? It's the space and time. So if this is a constant of motion, of course, something else has to change, no? In order to compensate, which is the angle and this affine parameter. Then I solve it from 0 to phi max, and I just integrate it. And then, of course, now this result depends on h. Well, h is not a constant. H, initially, you can play with it. You can say, hey, let's put h to vary like this, or vary like that, or let's see what happens if, let's say if we put radiation-dominated universe, for example, what will happen if it's matter-dominated universe, what happens if it's, so it depends, no? So initially I did this expansion, which is the standard, and I obtained this horrible resolution, which is an error function. It's a standard mathematical function. Qualitatively behave well. It still is telling you that the UV modes, they don't contribute to the integral so much. Well, it's not what I wanted, because what I wanted is to obtain exactly the result, which is observed. Let's say when you find the textbook, for example, I think I wrote it somewhere here. In the textbook, you find this. Dun, dun, dun. So I wanted to obtain this, exactly that. Then, for obtaining that, h has to change like this. But then after I realized that actually that's what h, the whole parameter, more or less change in each epoch of the universe. Of course, now, I was discussing with a friend who is now well, he's with Slack doing the data energy survey. I was explaining him this. He argued, but you isolated the epochs of the universe. What happened? You mix them. Well, that's an argument which I didn't touch it. I have to see that after. So this is one critic I received from them. But at least if you isolate each epoch of the universe, the Hubble parameter behave more or less. This is a constant. This is one word. Then when I impose that in that integration, then I obtain this result. And when you impose that result in the integral, which comes from the 0-point quantum fluctuations, when you impose it here, you obtain this result here.
So this is where I was something like, because the angle you derive is basically like how much you produce particle can travel from the band. So why do you put in this upper bound in the k-space calculation? Because in that case, this integral for the k-space is not the same as the span of your angle in your real space.
So you're talking about how do I convert from the position space to momentum space, or
Yeah, so why do
Yeah.
you choose theta vector?
there is an argument which I didn't include here, and it's a little bit you can debate about that, but I impose uncertainty principle. So because I convert this integration here, where is it? Here, this integration will be on time at the end. R will be fixed because in these coordinates. So I use the energy time uncertainty principle. So time goes like 1 over energy and energy scale like k. And then that's what I use for integrating that. Of course, you can say, it's naive, but well, that's what I did. And then that's how the results came out. Of course, more formally, you have to do maybe a Fourier transformation. Or, I mean, you want to be more rigorous mathematically. You could be more rigorous mathematically. Well, as a first calculation, I think is good enough. Then that's what I did. I mean, precisely you have to convert from if you do in static coordinates, you have to convert from position to momentum because the integral is in momentum space. If you are in the Friedman-Lemaitre-Robinson-Walker, which cares more the time evolution, you have to use the energy time uncertainty principle in that case. Then it depends. Of course, both you can have the seater, and this is a debate we have with referees always. Or every time when I wrote a paper before, and I wrote the seater metric in a static coordinates, the referees always reply, the universe is homogeneous and isotropic. I say, yeah, I know. Well, this is a static coordinate system. If you do a coordinate transformation, you obtain the Friedman-Lemaitre-Robinson-Walker, exactly with the exponential factor which accelerates the universe. No, it's another way to represent. It's different coordinate systems, but they represent. Well, of course, that's why by purpose I don't touch the static case here, precisely. I don't show the Friedman-Lemaitre-Robinson-Walker, but in the static case also the same results emerge. Then I have some confidence in this result, but of course we need something more solid, no experiment or something. Then any other question so far here? Or
So could you impose the uncertainty principle that your upper bound on the real space converted to your lower bound in your momentum space, right? So
yeah, correct.
that's the opposite of what you wrote there.
Yeah. What do you mean? The opposite?
What you write is you convert to upper bound on your angular coverage into upper bound in momentum space.
So you mean, let's go here. You mean here? Or you mean before?
Yeah, here. So
here, well, here, this is K actually. This is not this is just K. Well, actually forget this. It's this one actually. It's this one. Okay. Well, this L is the beta I showed. There's an issue with the notation because this L is the beta I showed before, is the angular momentum. This is K squared. This R is fixed. You don't touch it. So this is telling you when K is large, what happens? We are in the ultraviolet regime, no? UV. So this is more or less 0. It tends to 0. But when K is small, of course, this phi is as large as you wish. Now, you can say, it blow up. No, well, the angles repeat itself, no? 2 pi, 3 pi, 4 pi, whatever. It doesn't matter. The point is that it will give you some angle, and that angle will change like the inverse of K squared. And since when you include that in this integral here, this will go down. When you integrate the phi here, it will go down to like 1 over K squared, which cancel partially the K cube. So this is a way to reduce the modes.
So what means that here, since you write it as an upper bound in real space, so now you convert to lower bound in real space as an L cutoff rather than UV cutoff.
Well, I'm not so sure. Maybe we can debate later because now I cannot. I don't know so sure if I really understood deeply what you're trying to say, but there must be something there good to learn. So then the next is the issue of dark matter. Initially, I did a proposal which actually was debatable because, well, there was an editor choice and somebody did a comment and then I replied the comment. But the solution, the truth is that the solution of this paper is not a vacuum solution in the rigorous sense. It was not a vacuum solution. It's a vacuum solution if you redefine the time coordinate. Remember, the time coordinate defines the energy and defines the levels of energy. So then, of course, I wrote a subsequent paper here, but this one I was not happy with that yet. Then after, well, before mentioning the solution, now I really found the vacuum solution, the real vacuum solution. I will explain how to attack this problem. Normally, let's go to the spatial metric, for example. This is the spatial case. Every metric is an ansatz. Every metric is an ansatz. What we derive is this component and this component. This component we never derive. We impose it. We impose it. Actually, when we derive the spatial metric, we put exponential, blah, 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 exponential, blah, 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 r squared, omega squared. And we input this in the Einstein equations, we set equal to 0, and then we derive these two components. So we have some freedom here, let's say. And then, of course, you can derive the geodesics. The geodesics, you impose how to say, the symmetries. And this is what we were talking a few minutes ago. Timeline Killing vector, angular Killing vector. And this is the one form. These are vectors. You have to convert to one form, and they contract. And that's the conserved quantity. This is the conserved energy, for example. This is the angular moment conservation. And then at the end, all those geodesics are reduced to only this equation, which is an equation of energy, kinetic term, potential. And everything is analyzing the stability of the potential. Derivative of B with respect to R equals 0, trivial. And then, of course, in the Einstein gravity, we have this. This is constant. This epsilon is 1 for massive test particles, 0 for massless particles. This is the Newtonian term. This is the centrifugal term, and this is the coupling between gravity and the angular momentum. And of course, there are differences with respect to Newton because Newton doesn't have this term. Obviously, it doesn't have this term then. And of course, there are some differences between general relativity and Newtonian gravity, especially a short radius, no? When the radius is small, because of this cubic term. Then, of course, I was trying okay, and the plane of rotation is arbitrary. So it's my answer here is that a galactic scale we have to introduce a different symmetry, not the standard r squared, the omega squared. So my intended result was to get the Pauli-Fisher law and the scales of dark matter a la Mond, no? Modified Newtonian dynamics that suggests that the scales of dark matter occur at the geometric average between the gravitational radius and the inverse of A0. A0 is a parameter of modified Newtonian dynamics. Modified Newtonian dynamics is not a perfect issue, but it could do more or less good predictions for galaxy rotation curves. That's why people more or less pay attention, but it cannot reproduce lensing. Bekenstein and Milgrom, they try to reproduce the Tebes tensor scalar vector theory, but many people then debate that no, it has problems, another. I mean, and there are other proposals, non-local gravity. You'll find many in the literature. The point is that, okay, I wanted to see how to obtain these things naturally. This was my initial solution, which actually now I don't like. Because even if it looks promising, it didn't produce enough lensing. And in addition, as I told you, it was not a vacuum solution. But it was a good attempt. So the final results were like this. So I will skip a little bit. At the end, the idea was to introduce this ANSAC metrics instead of r squared zeta r in the Einstein equations, and then impose 0. And then what happened? Then I obtained this metric like this. And then when I derive all the same stuff and so on, I obtain this potential. And when I found the derivative of B with respect to R equals 0, you obtain, of course, after matching, doing a match with the results, you obtain more or less what you should obtain. You obtain the geometric average. This A0, actually, it finished being 1 over zeta. It finished being the inverse of this scale factor here. So, well, of course, since this paper, this result is not yet it's developed, but I don't want to talk about it so much because it still needs some tests. I will just mention the results. The results were to obtain the Tully-Fisher law, which is the tangential velocity to the 4 for GM A0, and obtain this. This radius you obtain by calculating the derivative of the potential with respect to R equals 0 and solving, and you obtain that from this potential here. These constants have to be fixed, C1, C0, C1, C0, and zeta. As I say, zeta finish being the inverse of the acceleration of modified Newtonian dynamics. And this was more or less the idea. Now, the scales of dark matter, as you can see, well, forget this scale. Well, you calculate the average between gravitational radius and R lambda is the scale of the size of the universe, 10 to the 26 meters. You obtain more or less the scales where dark matter emerge. It measures 33, Milky Way, Andromeda, blah, blah, blah. If you calculate these results with the mass, the baryonic mass of the galaxy, you put it here. And you take this like 10 to the 26 and calculate, and then try to check in the data where the dark matter effects appear. It will be more or less at this scale. Yeah. So before jumping now to more general problems, I would like to know if there is a question. Yeah, sure.
So in your case, now this matrix in a vacuum solution?
Yeah, now the idea is to derive the effects of dark matter. I forget dark energy. I crossed that page already.
So how do you know that this matrix not diffeomorphic to a central swatch?
Yeah, this metric is not diffeomorphic to a spatial. It has to be. You think it has to be?
Because you still have the same symmetry, but for considering diffeomorphic to spatial, right?
I'm not so sure of that, but if we can. I think you have to take into account that these components, this is not the inverse of this component. It's different. No, this scale appear here.
Yes.
So
our here is equivalent to the original area radius square rather than the original radius.
Yeah, exactly. What happened is that, of course, you can make a coordinate transformation because I asked a collaborator to check first, is the vacuum solution? Yes. Then after he did a coordinate transformation for putting in the spatial form, well, he didn't obtain spatial actually. So he obtained that this component and this component are not the inverse of each other. Actually, you obtain something different. So in that sense, it's not exactly spatial. So spatial is the only vacuum solution as far as the spherical symmetry is imposed. But I think if you change the symmetry, there is a chance that the solution might be different. Huh?
If we go back to you just area radius, it will be
yeah, if it's square R squared, then you go back to spatial. If theta is equal to R, then you recover spatial. That's the idea. Of course, I invite people to verify if they can, if they have time to check, and that's the purpose precisely of showing these results for you to judge it.
So are there any like conical singularity or other type of singularities in this?
I have not checked it, but it could be. But yeah, I know what you mean exactly because those are problems that some colleagues work, so I'm familiar with. So thanks for the comment.
So what was the answer? Is it Schwarzschild or not?
My answer is that I think it's not spatial because when you make the coordinate transformation, unless theta, if you make theta R squared, maybe. But if theta is a parameter, then and you make a coordinate transformation for forcing R squared to appear here, you will obtain that this is the inverse of this. You will obtain that this is the inverse of this. It's something different. It's not inverse. Actually.
There are more parameters, therefore there could be more coordinate singularities in this system than the original spatial. So I guess it does not guarantee to compare to the spatial metric.
Yeah, there's no guarantee for that.
There could be, I mean, if there are parameter singularities in the system, to be connection.
But locally, forget about singularities. I'm asking a local question.
So I'm just
Singularities. Absolutely no relevance in terms of this question. You're right. The global structure of the space could be different. But locally, This cannot be anything else than short.
I tend to agree into simple.
I mean, instead of theta r, just write gamma of r. Write any value function. I mean,
Yeah,
that's very symmetric. Yeah. Right.
Well, let's say that we have to test. Still, it's too premature to say. But the idea is instead, because I wanted that the angular momentum of this metric to be the tangential velocity, such that that's the conserved quantity. That was the purpose. Well, yeah, thanks for the comment. And we will verify this part. So, any other comment or question? So now we jump to spontaneous symmetry breaking. I will talk a little bit about internal symmetries, spontaneous symmetry breaking, because another thing which I worked and I did is to formulate the black hole evaporation as a mechanism of spontaneous symmetry breaking. Because you can derive a Lagrangian which generates the black hole evaporation also. So spontaneous symmetry breaking is a phenomenon in particle physics. Basically, this potential, you have a potential initially which is stable. This mountain doesn't exist. Of course, the vacuum will be here. You are comfortable. Let's assume you are sitting here. You are comfortable. But if there is an earthquake or something, you will fall from the chair and you will find another vacuum. So that's your second comfortable state. So the same happens here. You change the free parameters of the system. This stable equilibrium becomes a mountain. And then, of course, you are still here, but this is unstable. Any perturbation, any external perturbation measures go to any vacuum. Which vacuum you select, it depends on the direction of the perturbation. So this is before going to this. This is an example, for example. Ferromagnetism. All the magnets pointing in one direction. Why that direction? Because the external magnetic field, which is the perturbation, is pointing in that direction. If I put the magnetic field in another direction, it will be pointing in the other direction. So the standard Nambu-Goldstone theory suggests that the number of broken symmetries is equal to the number of Nambu-Goldstone bosons. Let's put it this way. What is a broken symmetry? What do you mean by broken symmetry? It means that the Lagrangian violates the symmetry? No. Actually, the Lagrangian still is invariant under that symmetry. In reality, when we say spontaneous symmetry breaking, it means the ground state is the one violating that symmetry. And the effect of a broken generator, if you apply over a vacuum, is mapping that vacuum to another vacuum. It shifts you to another vacuum. That's the effect. That's why it doesn't annihilate the vacuum. That's the reason. Now, in general, a Lagrangian is kinetic terms minus potential. This minus sign is important because the Lagrangian is a relativistic invariant. It's the difference with the Hamiltonian. The Hamiltonian is not a relativistic invariant. And then some of you are bachelor. Question of every bachelor student: when to use Hamiltonian, when to use Lagrangian. You use Lagrangian when you are in relativistic regimes because you need a relativistic invariant. You don't want to deal with a Hamiltonian, which you have to convert with a Lorentz factor for doing physics. The Lagrangian, you don't have to convert because it's already relativistic invariant. That's something important. The point is, we have this potential, and again, the equilibrium condition is the derivative of the potential with respect to the field equal to 0. You ignore the kinetic terms. In other words, this is the Euler-Lagrange equations ignoring kinetic terms. Exactly as simple as that. So this is the symmetries. Of course, we apply unitary operators. The exponential of I, Q is the generator of the transformation. So in the ordinary vacuum state, when there is no spontaneous symmetry breaking, that charge annihilates the vacuum. So it means that if you apply this unitary operator, you will leave the vacuum invariant. But when the symmetry is spontaneously broken, this is what happens. Okay? There are plenty of applications. People do superconductivity with these theories, ferromagnetism, etc. So there was a problem addressed by Hitoshi Murayama, who who is in Berkeley. He was the director of the IPMU until for many years, actually, when the IPMU was at its best. Not right now, actually, it's falling a little bit. But let's say by the time these guys studied that the number of, let's say, the Nambu-Boston theory is not satisfied in condensed matter systems. Let's say the number of broken symmetries is not equal to the number of Nambu-Boston bosons. The relation is 2 to 1. Sometimes there are 2 broken symmetries related to only one gapless particle. And they explore all these systems where I believe this happened. Then I decided to explore the problem, and I realized that the quantum jam-buster equations could address this problem. And how is that? First of all, when you have another parameter of the system, of course, the vacuum expectation value of this guy is different from 0 when the symmetry is broken. But if you sum all the possible other parameters, this vanishes because it's like summing all the vacuums. For every vacuum, there is a diametrically opposite result which cancel it. And that was a key point for applying this triangular formulation, which I proposed in I think 3 or 4 papers. The idea is one Nambu-Boston boson, another Nambu-Boston boson, degenerate vacuum. 3 lines almost parallel to each other because we are in the infrared limit, and they obey jam-buster. Of course, jam-buster means that this slope is maintained exactly the same. This slope is exactly the same. These two representations, these two are representations of the same event. 2 Nambu-Boston bosons interacting. Now I exchange them n to n prime, so I inverse the lines. These are the same event but inverted, no? Inversion of the event. In the thermodynamic limit, of course, they become 3 parallel lines, more or less. This is equivalent to this double commutator. If you expand this double commutator, you obtain these 4 triangles. How do you do it? Well, you have to expand this, assuming Lie algebra. These are broken generators. This is the Nambu-Boston field, and this is equivalent to the vacuum expectation value of the other parameter, because this is Nambu-Boston field, this is the broken generator, and this is different from 0. But if you sum all the vacuums, this is 0, and this is what the jam-buster are telling me here. That's very well explained in one of the papers, the longest one. I think this is the longest one. It's well explained, that part. So group theory and spontaneous symmetry breaking is well, later I explain how to solve that problem of counting and so on. So we have a group. Of course, the vacuum is not invariant under the action of the total group, but there is a subgroup under which we have some invariance. So the dimension of the coset in general tell us the number of broken generators, and this tells us the number of Nambu-Boston bosons. But this is not true in condensed matter systems, where the relation is 2 to 1, and in addition, the dispersion relation of those Nambu-Boston bosons is not linear, it's quadratic. So omega is proportional to k squared instead of omega proportional to k. There are other systems where the dispersion relation could be different. Could be fractional, could be something. These guys explore all those cases, but I didn't want to explore that one. So I will mention briefly, because I didn't want to go so deep in this, is that when these 4 events are equivalent, the dispersion relation comes out to be quadratic, is explained in this paper. And it's not that the Nambu-Boston theorem failed, it's that the 2 Nambu-Boston, this n and n prime, becomes a single degree of freedom. They fuse in a single degree of freedom. That's the representation we have when these 2 events are equivalent, for example, because exchanging these 2 guys are the same. How do you do that? Well, this depends on the space-time. You assume a space-time translational invariant with some exponential here, and they become some phases, exponential phases, blah, blah, blah. And at the end, when you factorize all the terms, and you factorize the phases, and you impose the limit when the energy and the momentum go to 0, the energy goes to 0 linearly, and the momentum goes to 0 quadratically. And this calculation is done normally in the textbooks, in any textbook of quantum field theory. only that I repeated the calculation with this argument. No? So, but I didn't want to go so deep in that. Instead of that, I wanted to mention that exploring the analogy between black holes and condensed matter systems, of course, I explored some problems in Hawking radiation, but in addition, I proposed a Lagrangian for reproducing the Hawking radiation. This Lagrangian can reproduce exactly the spectrum with this potential, quadratic, cubic, quartic. 3 free parameters, And of course, the evaporation only occurs with m squared is smaller than 0, so it's equivalent to a mechanism of spontaneous symmetry breaking. So what I'm trying to portray is that the particle number operator is another parameter. Before the symmetry is broken, so it's 0. So it's before the formation of the black hole, where you don't see black hole. After the formation of the black hole, the observer see particles, is what happened here. So if you take that as another parameter, you can interpret this as a mechanism of spontaneous symmetry breaking. So it means the black hole is permanently looking for a stable vacuum state, but it can never find it. And that's why the evaporation process occurs. Of course, well, I assuming that the spectrum is thermal. Recently, with a collaborator, we explored the problem with more rigor. We found some non-thermal modes, but of course, because that calculation is from the scratch, from the Einstein equation itself, and considering other issues. But the standard calculation, for you to have an idea, what was it? Consider a scalar field moving around the black hole. You expand in positive and negative frequencies. And then, of course, before the formation of the black hole, you define one vacuum. After the formation of the black hole, you define a different vacuum. This is the vacuum before the formation of the black hole. This operator annihilates the vacuum. After the formation of the black hole, you can define this A as the annihilation operator. You can create your own vacuum locally, but when you compare these two vacuums, you will disagree. No? When you try to use that operator in this vacuum, of course, you will not see vacuum, you will see particles. No? That's what happened. This most people neglect because they go inside the event horizon. And the Hawking evaporation, of course, occurs. In order to compare the two vacuums, you need to use the Bogolubov transformation, which are these. And the evaporation process occurs is when this coefficient is different from 0 because it mixes the positive and negative frequencies. So I will mention it quickly because, of course, there is not so much time, but it's something I wanted to mention. And if you take the particle number operator as another parameter, it means that the sum of all the possibilities should vanish. But if this is true, it means that some vacuum expectation values are negative. And I didn't know how to interpret that. I tried to interpret that as the possibility of interpreting that as antiparticles, also emerging from the event horizon also. Is a possibility. But still, of course, there are a few publications about that. I have wanted to publish in better journals those one, but anyway. And now finally, I will go to the neutrino oscillation problem, which is also related to the symmetries in physics. And I will explain why. The neutrino mass, let's put for you to understand what is the problem neutrino mass. When Weinberg, Salan, and Glashow created the electroweak theory or discovered the boson C and W, gauged that theory, and so on, they believed the neutrino was massless. And you can see, if you study the electroweak theory, you will find that the neutrino doesn't get mass via Higgs mechanism. The Higgs doesn't give mass to the neutrino. But what happened? There was an experiment, the famous solar neutrino problem. They were expecting certain amount of neutrinos coming from the sun. They only detected, I think, 1/3 of them or something like that. And they didn't know what happened. And what happens is that the neutrino oscillates. It means that when the neutrino is moving through the vacuum, it changed from electronic to muonic to tauonic and So when the detector is designed for detect only a neutrino electronic, it will not detect the tonic or muonic. And that explains the deficit of neutrinos. That is because not all the neutrinos arrive as electronic neutrinos, even if they were born electronic. So neutrino is a particle which oscillates in flavor, change the flavor when it moves through the spacetime. There are three neutrinos, electronic, muonic, tonic, and this is the oscillation matrix. This is not invented. This is what the experimentalists use for measuring the parameters. I am ignoring here the CP violations. The possible CP violations are completely ignored because for simplicity, I wanted to analyze. And now talking about CP violations, there are two serious experiments, one in Fermilab, Chicago. They say CP violation is 0, but there is one in Kamioka, Japan, saying CP violation is maximum. So there is a totally discrepancy of those two serious experiments suggesting opposite results, and nobody knows what happened. So it's a very interesting problem. If you have time, you can take a look at it. This is the neutrino oscillation matrix. Of course, you have, I think you have here electronic, muonic, tonic, and the base 1, 2, 3 here. So in other words, you can express the neutrino in the phase 1, in the bases 1, 2, 3, and it will be linear combination of flavors, or you can fix the flavor and linear combinations of eigenvalues. Again, I interpreted this as the fact that the neutrino is oscillating between three different vacuums. In one vacuum, the neutrino feels muonic. In one vacuum, the neutrino feels tonic and feels electronic. Why it doesn't select any vacuum? Because the neutrino interacts weakly and it's a small cross-section, whatever, but it never selects a vacuum. If you are a particle, if your potential get the Mexican hat shape, but there is not enough perturbation for you to throw you away to select one vacuum, you will be oscillating between all the vacuums. You will be swimming forever there. Then, of course, but the neutrino is not a boson, it's a fermion, and the neutrino will be some kind of, you cannot see as the boson swimming around. It's most likely the flavor taken as another parameter. And that's what I did. I took the flavor of the neutrino as another parameter, then by using the arguments even without quantum Jam-Bastel equations, we know that if we sum all the other parameters, we obtain the trivial result, we can recover the ground state. If we sum all the possible vacuums, we obtain the original vacuum. And then when I impose this, there are conditions. I have to sum these three equations. This comes from the neutrino oscillation matrix. So I have to sum this plus this plus this. So I have to sum component by component. I obtain first component, second component, third component. These two equations are redundant. They are just shifted 90 degrees. You can see sine, cosine, cosine, sine, cosine, sine. And the derivative of this with respect to theta 1, 2 is this actually. And what I did by convenience, I changed the sign of all the angles because it looks more beautiful. So it's like changing the frame of reference, no? Then I impose only one value, theta 1, 3 here, theta 1, 3 time, and I derive theta 2, 3. First, if you assume that theta 1, 3 is 0, let's assume this is 0, this will be 1, and you will obtain that sine is equal to cosine. If you change the sign of the angles, it's equality. The sign difference doesn't exist. I will be 45 degrees. And guess what? I mean, that angle is almost 45 degrees. The experiments say that it has to be around 45 degrees, more or less. Okay? So now, instead of putting 0, I enter the experimental 8.47 degrees here. 8.40. I divide by cosine, and then it's tangent of theta 1, 3 equal to whatever. Then when I derive, I think I obtain 39 degrees or something. It's inside the uncertainty values, what is observed, because it's 45 plus minus 7, something like that. So it's still inside the values. And then after with those two values, I enter in one of these two equations. They will give me the same result, only shifted 90 degrees. And the experiments cannot distinguish between one angle and the other angle 90 degrees because the experiments of oscillation, they measure is sine square of 2 theta. And if you put sine of 2 theta, there is no difference between the angle plus 90 degrees. No? If you shift 90 degrees, you will obtain exactly the same result. So that's, and it's a square additional. then that's why I say that these two equations are redundant. So this cannot be seen as exactly as a rotation matrix. It's not a rotation matrix because the rotation matrix, the determinant has to be exactly 1, but when there are two redundant columns, the determinant is 0. So this is my point right now here. And then the point is that when I include the values, I obtain the 3 angles consistent with experimental observations inside the uncertainties. So, not the 3 angles, I obtain 2 angles because the first one I just impose it, 8.47. Now, the masses, the problem is the masses, how to find the masses. The experiment, I will tell you, the neutrino oscillation experiments right now, they just measure the angles, the 3 mixing angles, and they don't measure the masses. They just measure the difference of the square of the masses. So they measure m2 squared minus my squared, m3 squared minus my squared, m3 squared minus m2 squared. That's what the experiments measure. And m3 is much larger than m2 and m1 is normal ordering, and m2 is approximately m1. Then thinking a little bit, and a first exercise I did was a triangular formulation. And then each triangle, each size, has to scale like 1 over the mass. This means that when this angle is 0, these two masses have to be the same. And this is a rude approximation because when I sum these 3 angles, I don't get 180 exactly. I obtain more than 180. But as a first estimation, I work it in this way. I improved the calculation later, but I will not show that one because it still is in process. But the point is that when you do that, m is much larger than these two, and these two are almost the same value. And you can predict more or less m1, m2, and m3 consistent with what is expected. But the problem is that we don't know what is expected because we don't know m1, we don't know m2, we don't know m3, we don't know anything. We know the difference square. So in this part, we cannot say anything is too premature, but it's interesting that we can find relations between the masses and angles and so on. So, and this part, before closing the presentation, I must remark that I found something interesting recently. If I change the basis and I put intel 1, 2, 3 instead of electronic monotonic, theta 1, 3 is unchanged, it's an invariant. But theta 2, 3 and theta 1, 2 exchange roles. So I obtain 39 for the other and so in other words, they exchange values. And this is very strange for me. I mean, it means that when you take the flavor as another parameter, the results might differ, but only by the exchange of angles with respect to the fact of taking as another parameter the eigenvalues, or I call eigenvalues to 1, 2, 3, so in my language. So this is an observation very important, which I am reporting in a paper which was submitted last week actually. But I didn't show these results here. So I wanted to say thank you for the opportunity. First, there's no YouTube in China, but anyway, this is also an organization based on Macau. And now I want to do the conclusions. The real neutrino mass will come. It will come. I think it will come from symmetry arguments. It's obvious that symmetry will be important for that. We don't know what is the mechanism for giving mass to the neutrinos, but for sure it's not the Higgs, unless there is some kind of stereo neutrinos, but nobody has seen them. Quantum jam-master equations have a correspondence with Nambu-Wilson theory. Is something which I demonstrated before. Black hole information paradox might be solved through symmetry arguments. Of course, this is a matter of debate because everybody says something different. So at the end, you don't know who is right. And the cosmological constant value is obtained via symmetry constraints, and this is what we were discussing before. And the effects of dark matter, from my perspective, will come from deviations from the spherical symmetry at the galactic level. So it means, from this perspective, there is no dark matter, and technically we are just inside this scenario GR. Of course, this one is under scrutiny. Still, we have to to verify, but this is my talk today. I took like 1 hour, 30 minutes right now. So thank you. If you have any questions, let me know. Thanks, Sebastian, for the chance to talk. Sure. Any other comment or question? Or anywhere we can talk after?
But how is the symmetry arguments solving the information part? So,
Well, because I didn't mention that part. I mean, I just explained that the black hole evaporation process could be modeled as a process of spontaneous symmetry weekend. Then if I take the particle number operator as another parameter, I need to satisfy this condition, assuming all the possibilities. Then what this means that I can recover the original vacuum by assuming these guys. But the problem with this is that some particle number operators vacuum expectation value will be negative. Then how do you interpret that? And one interpretation, which could be, is that of course the black holes, the pairs, no? Particle antiparticle here, the arguments say that one goes here and the other escape, but sometimes can escape the particle, but sometimes could be the antiparticle, is what I think. And this, maybe when it's the antiparticle, this is called, or probably the information could be recovered. It's one possibility, but it's too premature to say, because my colleague, my collaborator Meta suggested something else also. So anyway, well, this is one possibility, and we are trying to unify the criteria to see. Every time we discuss about information paradox, it's very dangerous, because when you try to publish these papers, everybody has a different opinion. Then when the referee receives these things, it depends which referee receives them. But yeah, it's a good question. This is the argument. The argument is that in some of particle number operator will vanish, and then you will recover the original vacuum in that sense. Well, of course, since the spectrum is thermal, it will not carry information, whatever. But this is when you select one vacuum. Here you are assuming all the possible vacuums. And another thing is that if you analyze in rigor the black hole evaporation, you will find also non-thermal modes. Maybe in those non-thermal modes, you can see something. Another option is that we found recently that with the Hawking arguments, the black hole has a natural remnant at the end of the life, so it doesn't evaporate completely, and maybe that remnant keep that information. I don't know. So I mean, there are so many options, and people propose so many different things that well, anyway, you can explore. In the literature you will find so many things that people say. But this is one possibility, and I wanted to show. Yeah. Any other comment or question? Okay, if not, thank you very much. And thanks for sharing here. And the end is going.